So today we will start to look at stochastic dynamics. Okay, learn some techniques and learn some applications. So we have already done some, right? That was basically in the context of random walks. So we studied random walks as the simplest stochastic process. We studied unbiased random walk. We studied biased random walk. Those are the simplest stochastic processes. Okay, so if we wrote down, let's just revise the basic stuff we know. Remember that the moment we have a stochastic process. So the thing is, okay, let me just add a few caveats before I go forward. Okay, stochastic processes are mathematically quite challenging. Okay, so you need to have a good understanding of what probability is, and a certain basic structure of probabilities, and then comes the idea of stochastic processes. Okay, now of course the way I have taught both in the first month when we covered random walks, and now will be sort of will not really nowhere meet the expected mathematical standard of mathematician. It probably will not even meet the expected mathematical standard of physicists. So we are sort of working at a much more rudimentary mathematical rigor with the focus on building intuition and how to apply them. Okay, and if you want to learn better, I would certainly recommend that you read this book by Gardiner. The title of the book is Stochastic Methods. A handbook for the natural and social sciences. This is considered a sort of a golden handbook, truly. It covers a lot of ground in a rigorous way. When I say rigorous way, at a way that's acceptable to physicists. Okay, so certainly this is the book that you must refer to for a an acceptable formal level. Okay, of understanding stochastic processes. So what we do in the class will be more how do we use. Therefore, I'm going to ignore and will not be able to cover much things in a much more rigorous way. Okay, so with that caveat, let me now move forward. So we learned random walk, discrete time random walk. This was the example of discrete time random walk, where an individual moves to one step ahead or one step backward with equal probability, right? Okay, this was the process we learned. So the moment, anytime we learn a stochastic process, we ask standard questions. What is the mean? What is the variance, the second moment? And of course, one can ask, what about higher moments? But at the very basic, we must ask what is the first and the second moment, and then we must ask what is the correlation structure of the stochastic process, and then finally, how does PDF evolve? PDF evolution. Okay, so these four set of quantities, help us capture a whole bunch of basic properties of stochastic processes. And we learned the following: when it comes to mean, the mean displacement of a random walker was 0. The mean square displacement of a random walker, we found, we proved, was equal to the number of time step. Of course, here I have assumed that x0 is equal to 0 without loss of generality. Okay, so this is what we learned. We learned that the mean is 0, mean square displacement is equal to the number of time steps, and we also learned the PDF evolution. If Px of t represents the probability that the organism or the person who is doing this random walk, what is the probability density function at xt coordinate. So we showed that this follows basically the classic diffusion equation. Okay, this is what we learned. Now, if I remember correctly, we never really spoke about correlations for a random walk, basic random walk. So let me first define a quantity called covariance. Covariance is defined as the following. You take the location of the individual at time t and you subtract it with the mean location, and you take the location at another time s and you subtract the mean. So basically xt is one random variable, xs is another random variable. Okay, so basically if you take the deviation of the xt with its mean and deviation of xs with the mean, and if you take the product of these two and take the expectation value, that gives us covariance. So basically what we have is covariance, what we really have on the left hand side is covariance between xt and xs. And instead of xs, I can replace it by y, another random variable y. But here we are looking at covariance between two time steps. So let us see what is this. Okay, now we know that the mean is 0, right? In this case, so this is 0, this is 0. Therefore, the covariance basically becomes a simple expression, which is xt xs. Okay, it becomes a much simpler expression now. And what is xt xs? Now let's make an assumption. Let t be greater than s. Okay, so this implies that we can write xt as xs, whatever the location animal was at s plus delta x of tau, where tau is t minus s. Is that fine? So animal was at location xs at time s, and then it has moved delta x in this additional time interval tau, and then the tau is basically nothing but this t minus s. Okay, so now let us substitute this expression in the covariance. So covariance xt comma xs, that is equal to expectation of xs plus delta x for an interval of tau. So what is the interpretation of delta x? By the way, delta x means what was the jump or the displacement of the animal in the following tau time steps times xs. So of course, now to follow up further, you need to know some properties of random variables. When you have a summation like this and the expectation value, and what you basically is, you can just take the xs times xs square. I'm just going to not do anything else right now. Delta x of tau times x of s. This is the term now. I have expanded it now. So now we have some expectation of two terms which are summed. That is same as summation of two expectations. Okay. Okay, fine. So far, I hope everyone is with me. Now, what is the first term? So since we have assumed that x0 is 0, okay, x square is nothing but the mean square displacement for time unit s. Okay, therefore, this is nothing but s, this quantity. Is everyone happy with this? So let's go back now to understand this. We said that the MSD is this, but x0 is 0, right? From this assumption we made. So therefore, mean square displacement is nothing but xt square, and that we know is equal to t. Now, therefore, mean square displacement xs square will be nothing but Yes, when we take the average. So that is this. Now what about this term? It's a product of, what is xs? Xs is a random variable. Delta x tau is also a random variable. Okay. And it's a product of two random variables. Now, and we have an expectation of product of two random variables. So now how do we solve this? How do we compute this expectation value? So let us try to understand this. This is time axis, okay? This is x, okay? So we have the random walk happening, okay? So let's say this was S. So we have reached xs here. And let's say this is tau. And then you reach t. And this is the value, xt. This was xs, this was xt. And this jump that has happened is basically this delta x of tau. Whereas xs is the location here. So what is this? So xs is a random variable and delta xs is also, x tau is also another random variable. How do you think these two random variables are related? Are they related to one another in some way? The delta x tau and x of s, are they related to one another? Think of the word independence. In the context of probabilities. So this delta x tau, does it depend on the value of xs?
No,
No, right?
it
Because
is.
at every, absolutely yes, for every time step after xs, the animal is still doing the same random walk. Every time step it takes like a forward or a backward step, right? So therefore the cumulative steps taken in the following tau time minutes has nothing to do with what was the value of x of s, right? So therefore x of s and delta x of tau are independent. So therefore, now let us go back and use that. So when we have expectation of two products, expectation of a product, and if those elements of the product are independent, then we can write it as product of expectations. Is that right? Because this increment is independent of the xs itself. What is the average of x of s? What's the average displacement after s time minutes?
0.
It's 0, right? So this goes to 0 and therefore the entire product goes to 0. Okay. So therefore the covariance between xs and xt is basically s. And more generally, so just go back here, we assume that t was greater than s. Okay. And if t was greater than s, we got the answer s here. If s was greater than t, what would have s was greater than t, what will we get here? We would have gotten t. Okay. So a more general answer is that it's actually minimum of s comma t. So the covariance between two displacements xs and xt is the minimum of s and t. Okay. Any questions? Okay. So why did we do this? Because I said that whenever we have a stochastic process, think of these 4 quantities, and we had done 3 of them, but we had not done the correlation. So I have just done that. Okay. Okay. So there's one more thing I have to now say, which is very important, which is that I have defined something called covariance. But what's correlation? Are correlation and covariance same? They're not same. Correlation is covariance between 2 random variables x and y divided by sigma x times sigma y. Okay. So I will let you calculate. What is the correlation between xt and xs. Okay. But this already captures the basic idea though. One thing to keep in mind is that correlation is bounded between -1 and +1. Okay, whereas covariance has no such bound. Okay, covariance actually does have a bound. It is bounded between minus sigma x minus sigma y on the one hand to plus sigma x plus sigma y on the other extreme. Okay, whereas covariance is convenient in number, bound between -1 and 1 for all types of random processes. Okay, so that is just a quick summary of the random walk. It is also a quick summary of a small new calculation about correlations. Okay, any questions before I go forward? Let me just also quickly revise one more thing, which is biased random walk, which we defined as follows: x of t was xt minus 1 plus 1, xt minus 1 minus 1 with probability p, right? And with probability q such that p plus q is equal to 1. So we define this. Okay, again, let's just recall what all we found in terms of the basic properties of moments. The mean was, p minus q times t, if I'm right. Is that right? The mean means displacement is not 0 anymore. And we also found mean square displacement with time. So I had given this an assignment or some work. I have forgotten now. I think this has a t term with some coefficients. Okay, it also has coefficients of p and q with t square term. Okay, so we have both linear and a quasi. Unlike the unbiased random walk, which had only linear term. Okay, this was this. Okay, now I will leave it as an exercise for you to find out what is this. Always think intuitively. What do you expect? So that's stuff always useful to think. Okay, and then what is the PDF for this process? And that followed the following equation, right? It followed right? So where V represented, this is Q, and then D is the standard diffusion. Okay, this is also called the drift term. Okay, whereas this is the diffusion term. Okay, this entire thing captures what is called drift. Okay, drift is something that is going in sort of one direction, whereas diffusion is something that's going in the spreading randomly. Okay, so typically when we say drift, it often has a sense of directionality, or a sense of deterministic nature to it. So for example here, right, the x minus x and mean displacement has this, it's increasing with time, meaning the animal is going in some direction, right? So that's what the drift term usually captures. And then we have a diffusion term that captures more about the randomness. Okay. Okay. So in some, again, if you go back, so this can be thought of as a dynamical equation for the state variable x. Okay. Whereas this is the description of the, not the state variable, but the probability distribution of the state variable. Okay. And the equation that governs how the probability distribution changes, as we have already learned, we call that master equation. Okay. And there is another name, and in some limit, it's also called Fokker-Planck equation. Okay. Is in general the equation that governs the temporal evolution of the PDF of the stochastic process. Okay. And the master equation does the same. Master equation is the complete equation. And typically when you go from master equation to Fokker-Planck equation, we have made some approximation. Okay. And that I will cover in the later sort of classes. And again, if somebody asks, what is the Fokker-Planck equation for a random walk? That would be diffusion. That's the diffusion equation. And what's the Fokker-Planck for walk? That's the drift diffusion equation. Okay, so those are some simple terms to keep in mind. But the drift diffusion equation is also used to mean slightly different things in different contexts, but broadly they all mean the fact that drift something represents something deterministic or an average. Okay, deterministic or average, whereas diffusion is variance or stochastic component of the entire process. Okay. Any question before I go forward?
So I didn't understand what correlation tells us about the stochastic process.
So correlation, so if you think of in the most general way, the correlation between any two random variables. So think of x and y are two random variables. Okay. So for example, x could be rainfall. Okay, y could be temperature. So they both are, you can, let's say you have that for every day, there is some value of the rainfall, the average rainfall value xt, that's the rainfall value on the tth day, and y is the temperature, average temperature on the tth day. Okay, so these are two random variables, right? So correlation captures, is there any relationship between them? Okay, this is actually a strong statement. I know it, it only captures some types of relationships, not all types of relationships. Okay, specifically it only captures relationships that are non-monotonic, that are monotonic. Okay, so let's take this example. If x was the rainfall and y is the temperature, if the data looks like this, the correlation, you expect the correlation would be close to 0. Okay, on the other hand, if the data look like that, then close to 1. Okay. On the other hand, if it was this, we expect correlation to be close to -1. Okay, so of course, why did I say it doesn't always work? Now consider a scenario like this. There is a relationship, but if you do correlation, it will turn out to be 0. Okay, so it only captures non-monotonic relationships. But of course, if you do correlation from here to here, it will have a strong correlation, positive and strong negative. But if you take the entire curve, it will get 0. So this is what correlation captures for any two random variables. Okay. Now what we were doing in the case of random walk was we were not taking the position of an animal with the position of another animal. That's not what we were doing. That's, of course, one can do that as well. We can also, what we were doing was something called autocorrelation or autocovariance. The word auto comes from the fact that I'm looking for correlation of the same random variable, except that now I'm looking at what happens when they are separated in time. It's the same random variable, but they're just separated in time. So in such a case, what does this measure? This measures if the system, if the random variable has memory. Has some sort of memory. That's what it captures. So when you apply the correlation for the same stochastic process, and you're looking at two time points separated by some window, and then you calculate, then it tells you how is the random variable at time t dependent on random variable at time the same random variable at another time s. Okay. So now what you can also do is the following, right? A useful quantity in such a case would be so this is the time lag, for example, t minus s, and this could be the correlation or the covariance t. You choose what works for you, and then you can plot this. If it's a line like this, that means they're strongly correlated no matter what the time gap is. But usually what you expect is something like this. As the time gap increases, the memory in the system decays. This is usually what you expect. And what we found in the context of random walk was the following, right? We found that if you take this xt xs, it's basically the smaller of the two that will have the value. That value will be the covariance, but the correlation, as I told you, I did not calculate. You should calculate it on your own and then see how that depends on the time interval. Okay. So it would be a useful exercise to calculate what is correlation for random walk separated by tau. How will this plot look like? Okay.
Yeah.
Is that clear? Okay. Okay, so now I'll move on. So let us now, having learned some basics of, is that correct? Some basic, revise some basics of stochastic process. Now we are sort of equipped with, what to do more, which is we will now do stochastic population models. Okay. Stochastic, it means to be more precise. Stochastic mean field population dynamics. So when we defined the contact process, what we did was we developed a a spatially explicit stochastic update rule for how individuals undergo birth and death, and then we did a mean field approximation, right? So this is now, we're not doing that now, we're doing something different. Okay, this is a different approach to modeling stochastic process. Now, what are the classic population models we know? We know the logistic model. Okay, and we also know, this is just to give example, a model with harvesting, right? Or a predator-prey model. So we have studied these models really well now in our course so far, in the previous course and this course. Okay. Now, if somebody asks you, these are all nice mean field models, but let's add more realism to this. How do we add stochasticity? Okay, there are now two ways to add stochasticity to above class of models. The above models. Okay, now there are two ways to do this. One, actually three ways. Let's now, one class would be called ad hoc introduction of stochasticity. You can also say maybe, phenomenological, although I'm not very sure if it's the right word. Okay. Now another one is based on first principle derivation. Okay. So what do we mean by these two approaches? Okay. Now let us first go back and think, how did we even write down these models? We have had a discussion on this point already in the class. So how did we even write down the logistic model? The logistic model was written in a sort of semi-mechanistic, semi-phenomenological way, right? So we argued that the per capita growth rate must decay with the population size. That was the basic argument because of intraspecific computation. And we wrote down an equation that meets, basic equation that meets this. Okay. And that was the way we wrote down, right? But now you also remember when we also began, remember the way we began the full stochastic spatial model, the contact process, right? So we defined all the probabilistic rules and then we derived the mean field approximation for that. That also had the same mathematical form, a linear term in n minus a quadratic term in n, right? Okay, so an example of a first principle derivation would be starting with contact process and doing a derivation of mean field approximation, right? So that would be an example of first principle derivation of a mean field model. Okay, so we started with these rules, right? 0, 1 goes to 1, 1, or 1 goes to 0. So with that, we arrived at how rho dot is 2p minus 1 rho minus, I forgot now, p rho square, right? So we arrived this equation. So this, we derived it based on the mean field approximation. So this would be a first principle derivation of the mean field model. Whereas the way we did in EC201, right, where we argued that the per capita growth rate must follow this kind of a curve, and therefore I write down n dot is equal to Rn into 1 minus n by k. So this would be a semi-phenomenological or semi sort of mechanistic approach, right? Okay, so likewise, just as there are two ways to write down a mean field population dynamical model, one this way, one this way, the same applies to stochastic mean field model. We can write them in two ways. Today we will go only stick to the ad hoc introduction or the phenomenological introduction, of stochasticity. So there are now two ways. So that's what we will do. So the basic way of introducing my regular problem, I'll redo it. So even here there are two ways. You have to decide where is the stochasticity coming from. Okay, in attack stochasticity, we often start with a model, for example, the logistic model. But it could be more generally n dot is equal to f of n. So we start with the model. Oh gosh, this is really annoying. See. Okay, so I hope it doesn't happen again. And then, so we ask ourselves, what is the origin of stochasticity? If the origin of stochasticity is environmental, we typically are something entirely exogenous to the internal dynamics. What we do is we just add a noise term. Okay, where eta t is a Gaussian white noise. So what do we mean by that? Again, any stochastic process must have some properties, right? And the key of them are that the mean is 0. In this case, we have to define a mean. We have to define a variance. Okay, so the variance for this is defined in the following way. Okay, so whereas what this basically means is that, if I take two different time points t and t prime, the correlation between this noise is basically 0. If I take the same point, that is the only time they have a correlation, and the strength of the correlation is sigma square, which is also the variance associated with this. Okay, and this delta is what's called Dirac delta function. Okay, now I'm not placed, there's no way I can define what's Dirac delta function in this class. So if you don't know, think of this function as being 0 if the argument is non-zero, and it's infinitely large when the argument is 0, meaning when t is equal to t prime, delta is infinitely large. Okay, so that's the stochastic process we add. Okay, so this is the environmental or exogenous stochasticity. Okay, an alternative way is a parametric noise. Okay, now, which is an endogenous noise in some ways. So what do we mean now? Let's go back to the logistic model. We know that n dot is equal to Rn times 1 minus n by k. R comes from the birth and death processes. Oh, we can argue that R is a consequence of stochastic birth and stochastic death. Therefore, R must be stochastic. R is not a constant value. So therefore, let us do the following. So one will say R is equal to some mean value plus eta t. Now let us substitute that in the logistic model. So what do we get? N dot then becomes R0 plus eta t times n 1 minus n by k. So what does that lead to? N dot, the first part of the equation now looks like the a deterministic logistic model, and then the second part now looks like this: eta t n 1 minus n by k. Okay. I have to figure out a solution for this. Today it's happening at a frequency which is substantially more. Okay. Yeah. So here we are. So now this is the same old logistic model term, and then we have a random variable term, and then we have again the same term. Okay, let's denote this in a very general way: g of n times eta of t. Okay, so this is a general way in which more general way in which the noise can be added, and this is called a multiplicative noise. Noise model. Okay. I will explain this later. Okay, what do I mean by itotions? I will explain this later. So there are basically what I would like you to take you home from this is there are two ways you can add noise: environmental or exogenous. And if you do, you just add the term to the growth equation. This is also called the additive noise, because you're just adding to the growth function, whereas in the parametric noise, one of the parameters assumed to be stochastic, and therefore what you end up with is the strength of the prefactor to the noise term itself depends on the state variable, which basically means the strength of the noise depends on the state variable. Strength of noise is state dependent. Okay, so this is an alternative way of adding ad hoc noise. Okay, any questions so far? I'm just described how to add noise. Let me know if you have any questions. Any questions? Am I going too fast? Okay, no questions. Okay, I'll move on now. Okay, so I have introduced how to do two models. Let's now go forward. So today we will focus on the additive noise only. Additive noise models. Okay, so before we do so, let's do deterministic mean field. So let's say we have an equation of this type. We know that we define equilibrium by finding all n star that satisfies this, and stability by checking the slope of the function at n star. Okay, this implies it is stable. Is that right? Okay. So this is what we have learned. Now let us ask a very basic question. How is stability affected by noise? So let us ask this basic question. So what do you think? How do you know? So this is, you can think of this question as analogous to what we did for diffusion, right? So remember, we had the mean field model and we added diffusion to it. And then we asked, is the stability of the equilibrium changed by the presence of diffusion? Okay, so this is an analogous question. How is the stability affected by noise? How does stability, how does noise affect stability? That's the basic question we're asking here. So remember how we do stability analysis, right? So now the new equation we have is n dot is equal to f of n plus eta of t. Okay, this is the new equation. Okay, so let us look at the perturbations around the equilibrium. So let's say that n of t is equal to n star plus n, where, well, let me call it x to make life a bit easy, x, where x is the perturbation. Okay, now let us substitute this in the equation above. The left hand side basically becomes x dot, because the first term is a constant, just goes away. The right hand side becomes f of n star plus x, and the noise term remains the same. And let us now do a Fourier series expansion. And you have higher order terms, and then noise again. Okay, so what is the first term? First term is f of n star, which is the growth rate at equilibrium, that is 0. Okay, and therefore what we have is x dot under the approximation basically is, let us assume that n star was a stable equilibrium. So therefore let us denote f prime n by minus alpha, where alpha is positive. So we have x dot is equal to minus alpha x plus eta of t, where we have ignored order 2 and higher terms. Is that fine? Any questions? Again, just recall that if there was no noise, x dot would have been minus alpha x, which would have meant that x of t. So this would mean that x of t decays exponentially, right? Exponential decay of perturbations. So instead, now what happens with the noise? What happens? What do you think the noise will do? Will it change the stability? What's your intuition? Do you have any intuition for this? Now, what will noise do? So this term is pulling the system back to 0, meaning x is always trying to go to 0 because of this term, right? Okay, what is this term doing? This term is just adding a kick And that kick could be either in the positive direction, right? It could be either in the negative direction because the mean is 0. Okay, that's what the second term is doing. So what do you think the effect, total effect will be? No guesses? Come on, people, you have to speak up a bit. You have not
There's no
spoken a
qualitative-
single, huh?
There is no qualitative change.
There is
It-
no qualitative change. Okay, what do you mean by that?
So the equilibrium will still remain stable.
Okay, so let's make a guess. Okay, let's get some intuition. We have been writing too many equations since the beginning of this class today. Okay, so this is the y-axis. This is time t. Okay, and where is 0? 0 is here. Okay, let us say, in fact, I started 0. Say perturbation was 0. I was exactly at the equilibrium. Okay, that means now the first term just is 0. What do I have now? X start is equal to eta t. That means the rate of change is some random function now, right? What will that do intuitively if I am at 0?
Fluctuate around 0.
It will make me go away, right? It made me go away a little bit. And then what does this term now do? The first term, it tries to pull me back, right? Whereas it tries to kick around randomly again. So now there is a tension. Now the deterministic term will want me to come back to 0, but the stochastic term doesn't care. It can push me either this way or this way. So whether I come back or go further up depends on the net effect. So it's possible that I may actually go a bit further, but maybe not as much. And then maybe next time when I am far away, this effect has increased. This is now pulling back even more now. It's alpha x has increased, right? Now again, this is doing the same thing. So, but it's possible that the net effect is now here. Okay, so likewise, so what will happen is, there are lots, you can't go back in time, sorry. Okay, so this sort of a behavior you can expect, right? The question is, if this is 0, right? This is the equilibrium, right? This is x in the y-axis. Okay, equilibrium is this. So question is the noise sufficiently strong that it actually will eventually win? Or is it that the deterministic term is sufficiently strong that we come back and only fluctuate as Arshad guessed? So will this happen or will this happen? That's the basic question one can ask, right? Is the question clear? So of the two, Arshad says that I don't know, Bevan, Arshad, I don't know who said. He said it actually will fluctuate around the equilibrium. Is that what most of you think will happen? Okay, no answer.
Shouldn't it size of the perturbation?
Size of the perturbation doesn't matter. Yes, that's a very good thinking. It may matter, the sigma, right? The strength of the perturbation may matter. Maybe there is a value of sigma below which it actually fluctuates around like this, maybe after which it actually goes off, right? That's a possibility. Any other thoughts? Okay, it's a good point. So let's now understand this a bit. Again, remember, what all should we understand about a stochastic process? Mean, variance, correlations, and finally, the PDF evolution. So we must understand all this. Okay, let us see what happens. Okay, now here is the equation. This is the rate of change is minus alpha x plus eta t. Okay, now it turns out that mathematicians do not like to write a stochastic process like this at all. Okay, now what is the left hand side? Left hand side is a rate, dx by dt, a differential, right? It's a concept from calculus. The rate of change is a concept from calculus. Now, if you want to write a rate of change as a function of something on the right hand side, every function must be a smooth function. Okay, that's one of the criterion for defining a differential equation. So we know that alpha x is certainly a very smooth function. No, x is a well-behaved function. It has nice derivatives. It's continuous, right? What about eta t? What is eta t? If I were to draw, so if I were to draw eta as a function of t, let's say at time t is equal to 0, somehow I force it to be 0 here, okay? Let's say the next time, of course, we're talking about continuous time here, so the next time doesn't actually make sense. Let us hypothetically say, okay, some finest, smallest possible interval. Let's say if this is here and this is here, where will this be along this? You know, it's a Gaussian random variable. It could take any value between minus infinity to plus infinity, but most likely take some value between minus 3 sigma and plus 3 sigma. All of you agree with that? Is that fine? With a 99% probability, it will be between minus 3 sigma and plus 3 sigma. Let us say this was the value it had at the next time step after 0. Now let me think of another smallest time step. What value will it take now? It's a random number. It has no correlation with what happened in the past, right? It doesn't care what happened in the past. It will pick another value which is totally random, again between minus infinity plus infinity with Gaussian distribution like this, right? So likewise, another value here again, another value here again like this. Now, if I were to make a trajectory of this, how will this look like? Will it look like a smooth curve, or will it look like a crazy curve? Does it have? Can you even define a smoothness for this curve? Think of intuitively. Do you think this curve will be a smooth curve? Or will it be extremely rugged curve like the Bangalore roads? Okay, so this will not be a smooth curve at all. It's actually not even a it cannot even mathematically define this function. It's actually mathematically ill-defined in terms of smoothness properties. Okay, so mathematicians don't like to write this equation in this fashion. They prefer a slightly different way of writing it. Okay, so this is something useful to know, because depending on the book, you may mathematicians, economists, they all write it in favored way of writing the equation is this. There's rate of change in the, they don't write rate of change, they just write the change, dx, okay, is equal to minus alpha x dt. So in a small interval dt, what was the change that happened? Plus dw of t. So they write in this fashion. They do not use differentials, they use increments instead. But the increments themselves are defined for extremely small time intervals, where now you wonder what the heck is this WDW, where d of w has the following properties. The mean value of d of w is 0, meaning the average increment is 0. Okay. And you should take average value is 0, this dw, are basically increments, right? Increments are independent. Meaning, if you take the the increment between t and t plus delta t and another time instant, another small interval, all the increments are independent, and that defines the correlations. Okay, now what about the variance? If you take an interval dt, and if you take the second moment of this one, the variance of this will be equal to dt. So this is how mathematicians define what are called stochastic differential equations. So what we have seen about is the physicist definition. This is the mathematician's definition. So, and W itself is called a Wiener process. Wiener was a mathematician who studied these processes, stochastic processes. So there is a slight difference in the way the mathematicians and physicists define, and they're both useful. And depending on the way you are thinking, one might be slightly more useful than the other. Okay. Okay, it's 5:10 now. So we still have to do a few properties, right? Mean, variance, correlation, and PDF. Because today's class has been maybe fairly mathematical, do you want me to stop here now? And maybe take up all these things on Friday? Is that fine? Because I wanted to think about this also. I didn't want to just listen to me non-stop. I think maybe when you will also do exercise on Friday, you will get a better understanding and cleaner understanding. Okay, so maybe should I stop here? Can you somebody please speak? My intention is not to overload with too much stuff, especially because it's mathematical.
Yeah.
Okay, shall we stop here now? Okay, so these 4 things we will do on Friday. Okay, cool. Thank you. If you have any questions, please feel free to ask.
Hello.
Yeah, please.
Yeah, I joined the class a bit late. Sorry for that. But I've looked at the notes on the one. I just
Sorry,
want to.
I'm unable to hear you.
Hello,
Yeah.
am I audible now?
Yeah. Actually, very faintly.
Just a second. I'll try to. This is a recurring issue for me. Sorry for that. Yeah, is it fine now?
Yeah, better, much better.
Yeah.
I lost you, Shrish.
Hello.
Ah.
Yeah. Yeah. Sorry for this. I'm not really sure.
Okay, I'm losing you again, Shrish, unfortunately. Okay. Anybody else? Any other person has a question?
So
the
is
next
the
1 month, let me just warn you, it will be slightly mathematical, okay? But we will combine with analytical stuff and then also numerical stuff. And I'll also try to make connections with how we apply these in real data. Hopefully all that put together will keep you engaged. Okay, sure. Go ahead. I think Sean had a question.
Yeah, so is the Wiener process defined similar to random walk? Because
Yeah, Wiener process is basically a mathematician's version of, it's basically continuous time random walk.
Right.
Absolutely. I mean, your intuition is perfect. Huh? Continuous. It's also basically a formal version of Brownian motion. Absolutely right. There's a chat box. So you can just type the question, Shrish. I don't see any questions so far. Yeah, any others? Anybody else has a question? But the W is a continuous version of ATAT NT. When you write NT, do you mean if you meant in the context of the Brownian motion? Yes, it is. Yeah, it is a continuous version of the what we discussed in the Brownian motion. So the increment in the, so basically the connection is that the increment in the Brownian motion is the eta t. So increment that happens in the Brownian motion is this eta t, and the actual animal location, the spatial location is the w. Okay, so increments are all dw or the eta t, and w itself is the actual animal location. That's one way to map the what you have done. Okay, cool. So I'll stop here. So